Hello everyone and welcome. Today we are diving into one of the most elegant solutions in data structures, AVL rotations. If you work with binary search trees, you know they can sometimes become loop-sided and inefficient. AVL rotations are the key to keeping these trees perfectly balanced for optimal performance. Let's see how we are going to study this. So, what is an AVL tree? An AVL tree is a self-balancing binary search tree where, for every node, the difference between the heights of the left and right subtrees, they also called as balance factors, and these subtrees must be 1, 0 or -1. Any other value means the tree is unbalanced, and that's where rotations come in. Let's talk about the core concepts in AVL trees. The first one is calculating balance factors, or known as BFS. The second one is node topologies, or unbalanced types. Now let's see what is BFS is. Before we rotate, we need to know where the imbalance is. We calculate the balance factor for every node starting from the insertion point, moving up to the root. The first node we find with the balance factor of 2 or -2 is our pivot. That's the node that needs to be fixed through rotation. Let's see what the node topology is. The rotation needed depends entirely on the topology of the three critical nodes: the pivot, its tallest child, and that's child. These are often categorized into three types. The first type is straight leg, nodes in a straight line. Second one is the dog leg. That's the nodes from a zigzag. And the less common type is spider leg. Even though there are three types, we usually only focus on the first two. Let's talk about the four types of rotations in AVL trees. The first one is right rotation. Our first type is the right rotation. This occurs when the imbalance is a straight line going down to the right. The pivot node has a balance factor of -2. This is the simplest case, requires single rotation. So, to fix this RR imbalance, we perform a single left rotation on the pivot. The pivot's right child, let's call it Y, becomes the new root. The pivot X becomes the left child of Y. This straightens the tree and rebalance the BFS. And the second rotation is left rotation. Now we have symmetric case, the left rotation. This is also a straight line imbalance, but going down and to the left. Here the pivot node has a balance factor of +2. And this LL imbalance is fixed with a single right rotation on the pivot. The pivot's left child, let's take it as Y, becomes the new root. The pivot X becomes the right child of Y. Simple single rotations fix all straight leg imbalances. Let's talk about the third rotation, the left-right rotation. Now for the dog leg cases, starting with the left-right rotation. The pivot is left heavy, BF of +2, but its left child is right heavy. So we have a zigzag pattern. To fix this, the LR requires a double rotation. Step 1. Step 1. We perform a small left rotation on the pivot's left child. This converts the dog leg into a straight leg. As step 2, we then perform the standard right rotation on the original pivots to complete the balancing. And for the last and fourth rotation is the right-left rotation. The right-left rotation is the mirror image of LR. The pivot is right heavy, BF of -2, but its right child is left heavy. This is fixed with another double rotation. First, the right rotation on the child, and the second, a left rotation on the original pivot. This fixes the right-left rotation setup. Let's see about the code and conclusion. Code implementation, rotation logic. Understanding the theory is one thing, but how does this look in a code? At its heart, a rotation is just a few pointer or reference assignment. The key is correctly reassign the parent, child, and any intermediate subtrees, like the subtrees in our examples, to maintain the BST properties. Next, the recap. When to use which? To quickly recap, if your imbalance is a straight line, a left-left, or a RR, you need one rotation. If it's a zigzag, like RR or RL, you need a double rotation to straighten it out first. AVL rotations ensure the lookup, insertion, and deletion operations, remaining all log n even under heavy use. And thank you all guys for watching me taking this step into AVL rotations. This is a fundamental concept for everyone serious about computer science. If you found this helpful, please like and subscribe, and let me know in the comments what other data structures you would like to explore next. Thank you.